Okay, in the section of alcohols, just to wrap up everything that we've done with this, just to remind you that if we just take a simple alcohol like this, what we're going to be doing is we're going to be, in the reactions that we've learned on alcohols, is primarily we're going to be exchanging it for something else, particularly the halides. Now remember, we're starting to give you reagents that you can use in order to achieve a whole lot of transformations in organic chemistry. They're not actually necessarily the best reagents. For instance, we teach you that we can use HBr to change an OH into a leaving group, and so then we get bromine, and we get that over there. So what are we doing is we're changing this OH for the bromine over here, and so the bromine is being replaced, and the product that we get is water, H2O, which comes from the OH and the H of those two things that have been combined. All right, so that's just one, and we can also do the same sort of thing with hydrogen iodide, and then we get the exchange, and so we get an iodine exchanging for the OH over there. And then one would think that logically we could also use HCl. And in some cases, particularly with secondary alcohols, it might be okay, but it really is not a great reagent. The better reagent to change an OH into not a bromine or an iodine, but a chlorine, is SOCl2, phenyl chloride. And it's just one of those things that you're going to need to learn as a reagent. Trust me, you're still lucky. There is a whole lot of reagents that you have not got to learn. So these are, on the alcohols, what I would call, these are our substitution reactions. Okay, all of these things on this side are substitution. And as you can see, all we're doing is using three different reagents, HBr, HI, and phenyl chloride, to change into bromine, iodine, and chlorine respectively. We don't need to know the mechanisms of that. There's one more acid, though, that we can use, and what we learned is that if we use H2SO4, and particularly in its concentrated form, we get the reverse of what we did in the alkene section, and that is we get dehydration occurring. That is, we're removing water, and what we're looking for here is an OH that has carbons next door. It's not a carbon that have carbons next door, and those carbons need to have hydrogens on them. So when this water gets removed, we get two options, two possibilities. The one is, both cases, is a double bond. The double bond goes to this side over there, and the other option is where it goes to the other side, like that. All right. So when the dehydration occurs, when we remove water, we're getting these two options. And the rule that tells us which one is preferred is named after a guy by the name of Zaitsev. So we want you to know that as well. It's Zaitsev's rule, and the major product is the one which has the more substituted double bonds. All right, so this double bond is substituted with a carbon, another carbon methyl group over there. There are three substituents on it, only one hydrogen. This double bond over here has one carbon group, it's actually an isopropyl group on it, and then it's got three hydrogens. Three hydrogens versus one hydrogen. So the least number of hydrogens equals the greater number of substitution. So major product and minor product. So you need to know that. You also need to know the mechanism of the dehydration, and we've covered that in class, but the mechanism is just the reverse of the addition of water to alkenes, which I've already covered.